Thank you for hosting this, Sergey. I think we are going to kick this fireside chat off with an important announcement. And
yes, we are very excited by this news because some of you may know that we are co-authors on a very famous Majorana paper from 2012. There's not a 127 authors on that one. Only 6 of us wrote that paper. 2 PhD students, a postdoc, a couple growers, and a professor. Well, the paper has been doing pretty well, scientific papers wise, and it has reached a milestone of being cited 5,000 times.
And this is something we want to celebrate.
Yes. So, Vincent, would you like to announce who is the winner?
So let's just quickly look at the stats that we didn't make this up. As you can see here, it is indeed cited 5,000 times now. So we use Google Scholar, of course. We don't need anything else. So here you see a bunch of papers. We ordered them by year, and you see that this one is the winner. So let's look at this paper. And ta-da! Sergey, who's the winner?
It's Professor Hao Zhang's group from Tsinghua University. He is the lucky winner of the prize for the 5,000 citation of this milestone paper. And of course, the prize, as we announced on social media, is the full collection of works by Jorge Hirsch. Jorge Hirsch.
In print.
Yeah, so I have it all printed here. This is the prize. I printed it all, and it will be shipped to Tsinghua University imminently after the conclusion of this fireside chat, because of course Professor Hirsch is the one who came up with the H index, and that's why a citation milestone will be celebrated with his collection of works, which is actually incomplete because of course Professor Hirsch keeps producing new works.
In any case, yeah, who is Professor Hao Zhang, Sergey? I think we need to do a deep dive, but yeah, for a bit.
I think before we go to that, there is some disclosures we need to make.
Yes, that is true.
We later looked again at Google Scholar, and somehow the number of citations has dropped below 5,000.
There is a mystery here.
So happened
I
here?
don't know, Sergey. Is it a calibration error, minor calibration error, I think, on the Google?
That would be consistent with Hao Zhang's type of activity, because there is a minor calibration error and then there is a nature retraction. But it could also be that 6 papers were retracted in the meantime, because we checked only 2 weeks ago, and the Majorana field is very active.
Surely more than 6 papers are in need of retraction, and likely they cite us. So who knows, maybe something happened. In any case.
Okay, so thank you for entertaining us with this, for allowing us to entertain you with this little skit at the beginning.
Let's look at something more serious, Sergey. So this person, Hao Zhang, is actually a retracted author from Nature, because he's the first author of this famous quantized Majorana conductance paper, infamous, I should say, which, you know, Microsoft is sort of denying any involvement with it, but this was already produced under Microsoft's umbrella at the time.
Yeah, hailed as Microsoft's Majorana qubits already in 2018, and in fact, it's quite unprecedented because there is 2 nature retractions. There's only a few people that had 2 nature retractions, and this is not a complete list because at some point the authors and the Microsoft collaborators stopped sharing data with us, and we couldn't investigate quite a few papers, maybe 20 papers. There's also corrections and expressions of concern published or in the pipeline, and perhaps future retractions. So this is, you know, going back 5 years or so when we started looking into these problems and when we had the first fireside chat about these problems.
Yeah,
Well,
so
Haojang is not only relevant because of this, of course.
this
This is
actually
a long segue into the events of last
last
week.
week. Yes. So, in all their wisdom, the Nature editorial team thought it was a good idea to ask Hao Zhang to referee this new paper by Microsoft. Because after all, he is an expert on lousy data.
Yeah, and this is very difficult to comprehend, this choice by Nature editors, because they know intimately the problems in Hao Zhang's own papers. But then, of course, he is one of the positive referees of this paper. And the paper had 4 referees, 2 negative, 2 positive. And well, if you remove Hao Zhang, which probably shouldn't be qualified as a referee for Nature, you will have 2 negative versus 1 positive. And that's the paper that was published last week.
And really, like, I couldn't, like some of you, if you may think that we're cooking this up, I'm making this up, but this is actually, it's not the case. It's go down in the Wayback Machine or so, and you can check this. It's actually, I don't know, I think some superior being is trying to tell us something, Sergey.
Yeah, we saw it when we saw Hao Zhang as the referee. I think we had some kind of nervous breakdown episode, like laughing hysterically. And anyways,
Anyway,
of course, yeah, this is all precipitated by Microsoft huge publicity push, and it was very confusing to many people because there was this Nature paper published, and not just Nature, there was also a roadmap paper that they published, but also a press release, and combine all of this talked about the creation of a topological qubit. And we're going to discuss it. We're going to discuss a topological qubit and what it is and what are the prospects of it. But we are obligated almost to start by discussing all these Microsoft activities. And something that many people noticed and Microsoft themselves admitted to is that the Nature paper does not demonstrate the topological qubit. The Nature paper does not have the topological qubit. And then on top of that and this is very absolutely unprecedented and extraordinary, that the editorial team of Nature felt compelled to clarify in the peer review file that they released that not only the paper does not have qubits in it, it also does not contain evidence of Majorana, which of course you need to have a topological qubit. So this is not like Nature editors clarify and comment on every paper that they publish. In fact, they never do that. Right? So this is really, really unique. Let's put it this way. This is a unique comment by Nature editors.
Yeah. Definitely. Yeah. What can I say?
So let's look at
I'm
this
still
paper maybe a
speechless.
little bit. I see you have it open. Let's start with
Yeah.
Nature because that's what we have. We cannot talk about hypothetical data that Microsoft allegedly have, where they
Yeah,
came
so
up.
this is maybe a good point to stress really for everybody listening in. This paper here that is now on the screen is basically the summum of the current achievements from Microsoft that are out in the open. And the rest is basically rumors, and some stuff might be shared in a month's time. We don't know. We will see. Okay.
Yeah, but I think one point we're going to make here is that if these are the achievements to date, it's just impossible, the news that they are coming up with for the future, right? It's just sort of building unreliable things on top of each other. So I don't know, Vincent, maybe we can look at just the data from this paper.
Yeah,
Because,
let's. Yeah. So
there is a lot of wordsmithing, like, as maybe some of you are not physicists here listening to us, or not physicists focused on this narrow topic. And it's easier to sort of lock into sentences, but it's easy to write a sentence that sort of like a disclaimer at the bottom of your plane ticket that you're buying, that the airline is not responsible for your death.
Yeah,
If the plane goes down, but just looking at the data is also very illuminating. So yeah, this is one of the sentences.
This is basically the disclaimer. I have a feeling this was put in there to please the referees a little bit.
Yeah, these kind of sentences are added as a wink, like, okay, we have to write it to pass some pesky referee, but we think it's Majorana. We're pretty sure it's Majorana because the whole paper screams it's a Majorana. We're measuring Majoranas, you guys. And why is it in nature? Ask yourself this question.
Yeah, of
I
course.
don't know if you want to show figure
Let's look.
3.
Yeah, I think this is
sort of the crux of the paper, right?
Yeah. So we see here on the screen, we see what is supposed to be evidence for a parity measurement. So it's a fairly, it's not the easiest measurement to understand perhaps, but basically what this line indicates is some sort of dynamic process in the device, some tunneling happening. And there's two different types of these dynamic events happening that they are detecting. And that is what this quantity here means on the axis. And you can see that it is fluctuating a little bit as a function of time. So there are two possible values. And this is supposedly evidence that this is the parity of a pair of Majorana fermions, this major word in the title. Now, this type of bimodal signal, however, in itself doesn't mean much. In all fairness, that type of signal, Sergey, how do we even know that it is superconducting?
Well, yeah, so this is my one of my points that I wanted to make in this fireside chat is that we understand even from Microsoft themselves that there is no qubits shown in this paper. We also know from Nature editors there's no Majorana shown in this paper. But when we look at these data, we also see no evidence of the narrow and very modest claims on the face of them that Microsoft is making in this paper. They're very technical and they're very buried in claims which have to do with parity and interferometry. So for parity, this switching up and down has to be transitions of the parity, which is the quantum states of the Majorana qubit. And that qubit is derived from some new state of matter, topoconductor, they call it. Everybody else calls it topological superconductor. But these jumps on the screen, they don't even show proof that this is coming from any superconductor, not even a topological one. And the word parity somehow means that it's something superconducting is jumping back and forth. But it could also be just a little charge, an electron jumping somewhere on this very complicated chip, giving this kind of bimodal signal.
Yeah, as long as some charge is jittering a little bit that affects the current in the device, you will get a bimodal charge signal. And yeah, this in itself, all it means is that there are two different charge configurations somewhere in the device.
And then the other thing is parity, right? Interferometry. So interferometry is a quantum phenomenon. If you studied quantum mechanics, you will know there's interference paths. Particle can take two paths around some kind of contour, and there is destructive interference, there is constructive interference, and that gives a large signal when it's constructive, small signal when it's destructive. And so you expect fringes or oscillations due to interferometry. And here we look panel 3H.
This panel here.
That's the proof of interferometry of something. So these are oblong aperiodic wiggles as opposed to interference patterns. As is tradition for Microsoft, the data is cropped. For instance, you don't see the 0 on the x-axis. It's actually stops at 2. That 0 that you see there belongs to the y-axis. There is no 0 on the x-axis. So what does it do from 0 to 2? What does it do for negative values? Why is it cropped at 13? Why is it cropped at 13? Why doesn't it go to 20 or 15 or 16? And this is pretty much the only plot in the entire paper that they show to prove that there is interferometry of anything happening.
And just to sort of like show you that interferometry, you know, this is just some paper from Nature from about 20 years ago. And here electrons are interfering with themselves. It's from the Weizmann Institute, this data. And here, you know, this is what interferometry looks like. You have nice periodic wiggles, you know. Now compare that
Yeah,
to this.
so you kind of see the progress in 20 years that Microsoft has made, right? From nice and clear interferometry patterns to these wiggles that, but what it amounts to is they don't show to a physicist a proof that something's interfering. And if you do, for a technical audience, a Fourier transform of these wiggles, it will look really bad. There'll be no one nice clear peak in these wiggles. And there is only 5 of them. So then, okay, now you can look back to the announcement that in the meantime, they have made not just 1 qubit, maybe even 8 qubits, but this is the quality of evidence of the interferometry, which is essential for the readout of this qubit. So this is, you know, to be analyzed. In fact, they released 100 gigabytes of data because in the past we were criticizing them for not sharing any data. So now there is sort of the opposite. There is all this data. And this will take some time to go through, but we will. But
Yeah,
what I
eventually.
want to point out is, okay, go ahead, Vincent.
No, I just want to say eventually everybody in the audience that wants the full technical unpacking of this paper, that is it's so much easier to claim things and put stuff online or even in Nature apparently. It's much more difficult to actually then completely unpack that and fact check it. But we
Yeah,
do
no, but this will be done for sure.
yeah.
But just think about it for a moment that if there is 100 gigabytes of data and these 2 plots we have on the screen, this noise and these wiggles, is the best data, right? Because you put your best data in your Nature paper. If this is your best data, you have nothing.
Yeah.
You have nothing.
Yeah. What can I say, Sergey?
Moving on.
Qubits. Yes, let's just move on. All right. So now, why does Microsoft claim that they have Majoranas in these type of devices? Well, that is because they claim to have a special trick that can tell them, like, we have a device, we measure some stuff, we run it through a computer, and out it spits, yes, we have Majoranas, no, we don't have Majoranas. Okay, that's what they presumably did here. Oh, I'm drawing on it. It's not necessary. Yeah, and we want to talk a little bit about that protocol, which they call the topological cap protocol. But Sergey, maybe shall we look a little bit how they make these Majoranas at Microsoft? How that's supposed to look like?
Yeah, absolutely.
Let me.
I can help you with that.
Thank you. I did that in Zoom. Thank you. So yeah, there's not a time and a place to go into great detail in this type of material system. This is extensively discussed in the literature, but the fundamental idea, and this is actually the same implementation that we're working on in Delft in essence, is that you have a one-dimensional nanowire, which is a semiconductor. You add a superconductor to it, and then you tune this system using electrostatic gates and magnetic fields, etc. You tune it into the right regime where Majoranas can exist in this device. And then at the endpoints in this device, this is a real device. We colored it afterwards artificially. In this type of device here and here, you would have your Majoranas. And schematically, it would look like this. You have one of these nanowires, and at the endpoints, you have your Majorana particles, so to say, your Majorana.
Yeah, so fundamentally, you always have 2 Majoranas.
Yeah.
You cannot have 1 Majorana, which is also funny because Microsoft called their chip Majorana 1, but you cannot have 1 Majorana. The minimum you can have is, well, I guess you can have 0.
Yeah.
That's the
Yeah.
minimum.
I guess. So they come in even numbers, in pairs, always in pairs. And they are separated from each other by a region that has this sort of energy gap. And that is the topological protection in a sense that they're talking about is that, to make these Majoranas disappear or fill each other, etc., you need to destroy this gap over the entire region in between the Majoranas.
And we should also say there are many different ideas for how to realize Majoranas. There's topological insulators, spins on the surface. There's even quantum liquids like helium-3. And this is just one approach that Microsoft is using, and also what is our specialty. So we are focusing on this one today for that reason.
All right.
We have the wiggle again.
Yes, I don't know how I keep doing that. I think it's sort of triggered by looking at the paper. I'm sorry for that. All right, let's now move on because this protocol that I was mentioning before that tells basically Microsoft claims they have a protocol that tells them for certain that we have these two Majoranas. And that was published actually a while ago in 2023. So that is by now, good almost 2 years ago and had been on archive for a while. This was announced in the March meeting in a very similar fashion to what is happening right now. They announced at the March meeting 2022, they announced that they found this very special way to detect Majoranas conclusively. That was first announced as a blog post on the Microsoft Azure Quantum blog, very much like it happens now.
Yeah,
And
it's kind of a deja vu how they do it, because I remember being at this March meeting 2022 and nobody could understand what's going on. There's no data. There's this announcement. We discovered Majoranas, you guys, for real. We have a very good way of doing that. There's been 100 experts who verified us, and all the same things they're doing again this year.
Yeah. And then eventually, like a couple of months later, they put this the first version of this manuscript on archive, and we had the chance to look at the paper, and what can I say? It was fairly disappointing. Now,
yeah, and there is an underlying reason, perhaps worth explaining also, that there are signals that are not coming from Majorana, but they look, at least initially we thought, they look like Majoranas. And the fact, the paper we started with, the 5,000 citation one, is wrong, because all those signals can be explained without Majorana. And this is why Microsoft, to address this problem, felt compelled to put forward this protocol, which they claim they find no false positives. If it's Majorana, if the thing says it's Majorana, it is Majorana.
So we have some news to break to you if you didn't pick it up on social media already. There's a first analysis has come in of this protocol, and this is done by a theoretician, Henry Legg. He's currently at St. Andrews, recently moved there. And what Henry has done, using his background as a theoretical physicist and his programming skills, he decided to do a deep dive into the software component and the theoretical basis of this protocol. Really, it's mostly code checking that Henry has done, honestly. And it's, Sergey, what can I say? It's absolutely stunning.
Yeah, so this is live since yesterday, late in the evening. So this is absolutely fresh, and it is also absolutely remarkable, because the level of analysis he went to is very, very deep. He really engaged with the code that Microsoft released under pressure, I should say. They released it under pressure because we were referees of that protocol paper, and we said there is no enough information to verify anything here. And so they found pretty amazing things. I mean, Henry Legg found pretty amazing things here that I think are also
So,
very easy to explain.
so it's we're not gonna again. This is not the time and place to do a deep dive into Henry's comment and all the finicky details of that. Maybe he wants to do that at some point himself. I don't know. In any case, but let's just look at some of the highlights. I don't know if we should call them highlights, but it's somewhat sad actually, if you ask me. Let's just look at some example. So Henry basically used the data that Microsoft had shared with the publication and their code to regenerate the figures from their paper, which he managed, which is good, I would argue. What you
Yeah,
can
you
see
can see on the left side here in panel 1,
this
where it says
panel,
device B, all these different colors. Maybe you can point at the orange color.
yeah, this one over here.
So this one is surrounded by the dark contour, the black solid line. And that is the output of the protocol. That is the region that Microsoft runs their protocol and says, this is Majorana. Okay.
And this
And
is
these pixels are in the space of magnetic field and electric field.
magnetic field, electric field.
Theoretically expected that Majorana is only appearing in some region of that space, in electric field and magnetic field. And so to find that region, then of course the idea is we find this region, we go there, then we make a qubit there. And
Yeah.
that's the idea. And so we need to know where Majoranas are.
So one of the things, one of the problems that Henry found is if he takes this exact code and he adjusts the range of the data to be fed into the protocol. So in this case, the range was from 1.4 to 2.8 Tesla. But if he now, for whatever reason, maybe because he fancied it or whatever, for whatever reason, you decide, let's analyze it using only the data from 1.8 to 2.8 Tesla. So we just check some data out in any case, right? Like, it's anyway not topological. Why do we even bother analyzing it? Let's.
Yeah, you can see the topological regions actually start from 2 Tesla.
Yeah, so why do we care about this data anyway? Let's just run it over this part of the data set and see what happens. The device is no
the
longer.
protocol does not find a region with a black contour around it. So the output, the outcome of the protocol is dependent on the range of the data that you feed in it. And Henry doesn't just notice that, he goes in the details in this comment and analyzes why this happens. And this has to do with the technical things like definition of the gap that's supposed to protect Majoranas is poorly defined in this protocol and other things. But I think this fact is very easy to understand. Microsoft is trying to convince us that we're learning something fundamental about the device that they have made, something that is invariant of how you take data. However, it is totally dependent. The output, which is supposed to be binary, yes Majorana, no Majorana, changes depending on data range.
Yeah. And that is something that should not have any influence on that. And there's another one in this category that I quite like. I'm scrolling over some stuff, and that's over here. So, and we can kind of understand it quite easily. One of the conditions, and that also illustrates the degree of arbitrariness of this protocol that Microsoft came up with. Basically, they define that if there are 7 pixels that fulfill their criterion, then we call it topologically non-trivial. We say there are Majoranas. And if you run that code, of course, when you now downsample the data, so this is the original resolution, but now if you use a downsampled version of the same data set, yeah, you don't hit the 7 pixels anymore if you're unlucky. And your device is suddenly no longer topological.
Yeah, so the 7 pixel criterion is absolutely arbitrary, taken out of nowhere. And in fact, you can also easily see that if you want more topological regions, you will make your pixels very, very tiny, right? You can take data with pathologically small resolution, which is the case for some of the scans where resolution is really, really tiny, to just have more pixels so you can call your stuff topological.
And maybe as a last, somewhat more graphic example to show, let's look at this one, Sergey, figure 7 of Henry's comment.
Oh yeah, so this is about
Yeah.
the false positives. So
Yes.
maybe I can try to explain. So actually, how do they define positives and negatives? They need something to compare their experiments with. And because they are trying sort of for the first time to prove Majorana rigorously, there isn't any data that's available that they can learn from, right? So imagine you have AI, you have a LLM, a model, but there's nothing to train on, right? There's no human language to train on, so it doesn't know what to say. So to solve this problem, they run a synthetic experiment. They run a numerical model, which they did not release the code, and they generate data where they can presumably know they have the background for it. They can know, okay, here is Majorana and here is not. Then they run the code on that. And that's how they say false positive, false negatives, negatives, positives, based on the synthetic data, not real experiments, but numerical experiments. And so in that synthetic data, one funny thing Henry noticed is they use a different version of the code. They apply a different version of the topological gap protocol to the synthetic version, then to the experimental version. And then what Henry does here in this figure,
And that is what you see here.
Yeah, he applies the
So in one here,
he applies the experimental version of the protocol to the theoretical
here,
version of the data.
yeah. So on the left here, where I'm hovering with the mouse, this is the theoretical version of the protocol that does not find any false positives. So this is real Majoranas. And then here on the right, he runs the experimental version of the protocol. Sorry,
Yeah, the other way around. It's the other way around. Yeah,
this is the experimental.
No. Actually, it doesn't matter because I think you can run the other one on this one.
So this region here is generated by running the experimental protocol, which is apparently more lenient and and somewhat easier generates positives. So that now indicates a region to be positive, whereas in the theoretical case on the right here, where the theoretical protocol was run over the simulated data, it was not indicated as a false positive.
But you can also see that the boundary of the other region, which kind of is present in both, the bottom region, is also changing depending
It's
on
also changing, so it can go either way.
In the grand scheme of things, it's a minor point, but it's also curious that it's changing by more than 7 pixels, by the way.
Now, perhaps the last point to make is that it is not surprising that all this happens and that this protocol basically, as you tweak it and as you play with its parameters, it can generate basically any outcome that you want. And the reason for it is that there is really looking at their data, and that is a point we made already almost immediately after we saw it, looking at their data, there is no reason to believe there are Majoranas in these devices.
Yeah, absolutely right. So I just want to point out that already 2022 we recorded one of these fireside chats where we just studied the version of this paper that was available on arXiv at the time, the topological gap protocol paper. And we did not go into all these issues with the code. Also, code was not available at the time. But we just looked at the data with our eyes. So to continue my LLM analogy, right? So you ask ChatGPT to generate something for you, and you don't copy paste it in your PhD thesis or something like that. You read it, that it made sense what it wrote for you at the very minimum, right? Maybe you shouldn't use it. There is some ethical discussion where you should or shouldn't use it, but if you used it, that's just a starting point, right? You use it to identify tumors in your body. You use not ChatGPT, but a specially trained AI to identify something very important. But then, would you like a doctor to take a look at the X-ray and confirm that the AI found the actual tumor and not just glitched because of something. So that's what we did, right? We looked at the actual data.
And that's like, so that is this example. You see here measurements at both wire ends. So this is, if you remember this schematic, this is measuring, oops, basically on either end of this wire in one of the Majorana, in one of the Microsoft devices. And yeah, this is then the data that you get. And Sergey, I don't know about you, but we've been measuring such data in our labs. Haven't you? Like, I have seen lots of the data in my Delft days. You have. I'm sure that many of the other.
So there is, I guess, no time to go over this in detail. Maybe we should also prepare our own comment, kind of like Henry's. We did put something on pub here, which captures a lot of it already, but the data are just like the oscillations, well, those wiggles from the Nature paper. These data are ugly. There's all kinds of stuff happening. There is no evidence of a gap. It's cropped, certainly in the bias direction, but also in the field direction. We don't know what happens at lower fields. There's maybe another 5 of such features. And the most dramatic thing that you look at is this bright yellow spot in the middle. That is the supposed Majorana signal, but it is not a perfect coincidence on the two sides. Remember, you have to have 2 Majoranas left and right, and they should really appear and disappear for the same range of fields, electric and magnetic. This does not happen in any of these data. They kind of come and go, and when they are both there, Microsoft says this is Majorana, but this is evidence of coincidence. But this is not evidence of correlation of the left and the right ends. And Majoranas come in pairs, and so there has to be a correlation.
Yeah, so to me, this looks like a somewhat a rather typical device that is pretty disordered, pretty messy, where there's, I think, lots of individual states floating around at low energy, moving when you apply magnetic fields. Some come down to low energy, create these signals. Sometimes there is a gap in the middle, sometimes there is not, doesn't mean much. It's, I suspect, a big conglomerate of what we call trivial states that are just moving in complex patterns around.
And another thing that's maybe underappreciated, certainly does not transpire through all the public communications that Microsoft initiated over this. And in the media, when they talk about topo conductor and this hybrid superconductor semiconductor system, to have Majoranas, to make qubits, to make multiple qubits, this has to be a really above and beyond in materials quality. And they are hiding this information, how they make these devices, how they process them. But what the data shows, just if you look with your eyes at the data, it shows very poor materials quality. Not an advance in materials quality that would be needed to make even one topological qubit. And one way I can show you this, perhaps maybe also using this paper. Do you want to go to, yeah, this is fine. So you see this orange region is in some random spot in panel 1, in some random gate and some random field as well. So for 1 qubit, you need 2 of these blobs. And while you can control the vertical axis for each of the blobs independently, you can adjust them separately. There is only 1 magnetic field for the entire chip, right? So the big golden chip that Ted Cruz was waving in the Senate a couple days ago, the Majorana 1, that goes into 1 magnetic field. There aren't the local magnetic fields that they have in their design. And so all of the orange blobs have to be at the same magnetic field. And you can see from the noise and the disorder in this data, then even if you can find 2 orange blobs at 1 field, as you add more and more orange blobs, like for 8 qubits, you need 16 orange blobs. You'll have a harder and harder time lining them all up. And that's the problem with disorder, right? Even if these were Majoranas, your disordered
which they are not.
conductors, yeah, these are not Majoranas. But also even making orange blob qubits, let's not call them topological or Majorana. Orange blob qubits will be harder and harder to make because all your orange blobs are a different magnetic field.
Yeah, anyway, why we are dwelling on this point, well, of course, Henry's comment is important, but first of all, this means that this paper in Physical Review B is not reliable. It is reliant on severely processed and likely cherry-picked data with many undisclosed processing steps there that are even internally not consistent. Okay, so this paper, you know, now we go into this black box of formal procedures, etc. Who knows what will happen? But in our opinion, it's very clear. This paper should never have been published or accepted by any respected publisher. And given that this unfortunately has happened, it should be retracted.
But I frankly have very low hopes for Physical Review B to actually do the right thing here. But I hope they
I'm an
consider all the
optimist.
comments.
I'm an optimist. I think something will happen. It cannot
Okay,
stand.
but let me play the devil's advocate, Vincent. Why are we talking about the 2023 paper? It's not relevant anymore. It's too old, right? We have the new Nature paper.
Yeah. So let's get to that. Give me a second to find the right line in the paper. Where was it written? Any case, I can't find the sentence, of course, when I need it. The point is that they use this exact protocol that we just looked at.
It's in the supplementary you can open. It used to be
to tune their device into the topological regime, so, or at least that's what they call. So here in the supplementary, there is some transport data. They have all these quantum dots, which, you know, they look, whatever, looks quite nice. This is some more details on how they set
let's just go
them.
to the TGP stuff.
This is the TGP stuff. Here we are. So this is
it's still in this Nature paper. It's just in the supplementary.
This is the basis.
The same orange blobs. Orange blobs are. This is what the Nature paper is based upon.
And here, yeah. So this is the exact same protocol, and yeah, we can completely anticipate that it's equally arbitrary and unreliable at finding Majoranas in this paper. So yeah, that is why this point is so important, that this PRB and Henry's comment and the fact that from an experimental viewpoint it all looks pretty mediocre, that makes us conclude that they cannot have well-established topological phases in these devices. They don't have control over Majoranas, let alone, and that is the end of it. That means there are no topological qubits, Sergey. It's
yeah, and given that the quality of parity and interferometry that they show in the Nature paper, there are no qubits of any kind, because, you know, another way to play devil's advocate is to say, okay, so maybe these are not Majorana qubits, but they are qubits, right? So we can study them. And this is perhaps a good point to mention that of course, this Microsoft lab is located in Santa Barbara, California, and literally next door, like you walk for 5 meters, is the Google AI Quantum Lab, where they have hundreds of qubits that are working, that are even attempting error correction right now. So you can criticize some of Google's work as well, as people have done. But the fact that they have more than one qubit is undeniable.
Well, exactly. I think nobody really doubts that they have a whole bunch of qubits. So I suggest, Sergey, that we are talking too much and too slow. Let's move on a little bit to what is the fuss about with topological quantum computing, okay?
Yeah.
So you want to have a step at in 1 or 2 sentences explaining what a topological qubit is?
Yeah, absolutely. So we already mentioned that it requires 4 Majoranas at the minimum or more, and that there is something about the physics, this gap that provides the qubit with topological protection. So protection against what? When people make press releases about this, they often dumb it down to saying that it can protect you from all of the qubit problems related to loss of quantum information, which is also known as decoherence. So qubits, their Achilles heel is that they don't keep quantum information. It goes away in a very short time, less than a second for most qubits, sometimes a thousandth of a second. That's all you got. And that means there's a lot of errors in quantum architectures. And so what that means is that there is a big hardware overhead on running quantum computing because you need to build more qubits to correct the errors. And so there is quantum error correction. There is quantum error correction, and then topological quantum computing is just a shortcut. If you do that, you don't have to worry about errors because it's topologically protected. That is what many people believe why this is interesting. And well, it is not accurate, at least not when it comes to Majorana qubits. You want to keep going, or?
Let's talk about this. I think this is an interesting aspect. So this is a more theoretical point in a sense that one of the fundamental criterions to be able to build a quantum computer is arbitrary control over a single qubit. You need to be able to make what we call the block sphere reach any point on the block sphere for your qubit. And here,
or it is also known as universal set of quantum gates. So to run an arbitrary quantum algorithm, you want a machine that can realize a universal set of gates.
Yeah, so let's not even talk about two qubit gates. Let's just stick to the one qubit, okay, Sergey?
Sure.
Turns out that with Majoranas, you can only do a very few gates, okay? For the expert, these are known as the Clifford gates. And if you've ever seen this qubit representation as a sphere, what it means, you can only reach these colored dots on the sphere. So basically all the extremes of the axis you can reach using topologically protected Majoranas by doing operations on them.
Yeah, that's why I wanted to make a little correction that you can do any gates, but only certain gates are topologically protected. Not all of the gates, and that's if you have Majoranas and the topological protection is perfect. There are no environmental issues at all. You can only do certain gates in a topologically protected way.
And yeah, what is interesting, this is a well-known fact actually, theoretically, like I think this has been known since the inception, and also within Microsoft, of course, the theoreticians there are well aware of this. That's no surprise for them. And part of their theoretical effort, this is just one paper I have here on the screen, is that find ways to find ways to do universal gates with Majorana qubits, sort of trying to retain as much topological protection as possible, but there's no way around. Ultimately, you do need unprotected gates. So
what you have to do is go back and forth a bunch of times.
Yeah, you can see that sort of here. That is the essence of the idea. You are assuming that your topological protection is perfect and lasting forever. And then you keep going back and forth, and you do small, unperturbed, unprotected gates in between. Sort of that is, I think, the basis of the idea.
This assumes that the back and forth, the vertical ones, are completely protected, so they cost you nothing. You can do 1,000,000 of them, and your qubit state comes back to exactly the same point. Absolutely no loss of decoherence on those. And if this is not your field, but you still want sort of more convincing, just open Google right now and Google Majorana error correction or topological quantum computing error correction, and you will find dozens of papers, and some of them are by Microsoft. You will find papers where they are conceptualizing error correcting codes for Majorana-based qubits, and then map it back to your previous belief that topological quantum computing is protected against decoherence. So it still requires error correction. And the best argument Microsoft can make about that is that, well, maybe if we had Majoranas, if we had Majorana qubits, and if they actually performed like hypothesis would indicate good, we could maybe scale our architectures with a slightly more favorable factor. So we would need fewer overhead qubits for error correction. And we would need, we could put more qubits on a chip or things like that, right? That's why I say 1,000,000 qubits on a chip. Of course, progress in other qubit platforms is not stopping. And so by the time Microsoft makes one Majorana, or I should say two, transmon qubits might become more compact. They make them out of new materials. The advantage that transmon qubits that Google and IBM and others are working on is that they're based on the physics, the physical principles that have been established 50 years ago and have been proven 25 years ago to work. And with Microsoft and Majorana, scientists like us, we're still working to find convincingly one pair of Majoranas.
Since you were talking about transmons, maybe it is important, I think, to zoom in on a particular problem that transmons actually suffer from. It is very, very well known to the superconducting qubit people. And forget even about what we just discussed, that there is a fundamental non-universality in the Majorana implementation of quantum computing. Forget about that. There is a whole other problem. The computational basis states that we use in Majorana qubits, in a Majorana quantum computer, if you wish, they are called parity states. So the qubit is parity even or odd.
Yeah, and that's why they put parity in the name of their Nature paper, because this makes it sound relevant to qubits, topological qubits.
Yeah, supposedly those are the two qubit states. Anyway, anybody that is active in the field of superconducting circuits in recent years know that there is an obvious, undeniable process that scrambles the computational basis. It is a problem to transmons, it can be, and other superconducting circuits, and it will equally be a problem to this platform of Majorana-based quantum computing. And it is what we call quasi-particle poisoning. And what it means is essentially quite simple. It is if anywhere in your device an uncontrolled, unknown charge tunnels into your qubits, any of them, or between your qubits in an uncontrolled fashion, you lost. Your computational basis has been scrambled.
Yeah, so your qubit or whatever circuit sits on a substrate, on some platform, and this platform is a material. It could be silicon, it could be something else, gallium arsenide, it could be sapphire. And there is a bunch of atoms. There's a crystal lattice of atoms, a layer of oxide on top of it because it was in the air at some point. And one electron getting trapped in that and jumping around and jumping onto your circuit scrambles both the transmon and the Majorana qubit, about the same way. And something like a cosmic ray, a particle traveling through space, hitting, you know how many, several thousands per second hit a square inch or something. Okay,
So, and is this entirely hopeless for superconducting quantum computing? No, this is something you can engineer and you can work your way around, etc. But it means it will be material dependent, platform dependent. So this entire exercise of understanding this poisoning time scale, what actually generates it, etc., at a material platform level, device level, needs to be. We have not even begun to understand that in.
Yeah, I guess one way to say it, Vincent, is that if I give you ideal Majoranas, ideal qubit according to some design, maybe Microsoft design, but it's really perfect. So first of all, not everything is topologically protected just at the fundamental level. And second, the limiting environmental factor is the same as the transmon qubit, which means combined together, an ideal Majorana qubit fundamentally cannot be better than a transmon qubit, which we already have. So is it worth even pursuing any of this?
You make it into an existential question now, Sergey.
Yeah, it's been an hour. Let's
let's move to the wrap up. Let me share this last slide. So since you put this question out in the open, is it worth doing? I don't think this is worth doing from a quantum computing perspective. Because as we spoke through this hour, we took a bit of a convoluted route maybe, but the points we wanted to make is that there is this whole stack that you need to achieve to be able to have Majorana-based quantum computing at the level of 1 million qubits. At the lowest level, there is no evidence that Majoranas have been controlled, have been tamed, that this is a beast that we know how to handle. It's
or
not even
created.
Huh?
Or created.
Yeah, we don't even know if they are there. Okay, so at this lowest level of the basic physics, the evidence is absent. And then as you go up through this pyramid, you encounter problem after problem, basically. So at the hardware level, at the materials level, for example, these are exotic materials we need to work with. They are difficult to grow, difficult to control. It is not easy to make these fancy topoconductors, so to say. And anybody active in this field knows that there's a lot of blood, sweat, and tears that goes into making these type of nano devices. And we can just go up, like the fact that there are no universal gates, the fact that even if you would somehow somewhat efficiently tackle that and be able to do quantum computing, you have the next decoherence mechanism, quasi-particle poisoning that you need to battle. And yeah, I just don't see it happening, Sergey. What is your take?
Yeah, I agree. I agree.
Thank you for once.
But I guess I'll be answering my own question at this point. Is it worth doing? I think for me, as a university professor, as an academic with my own research lab, it is absolutely worth doing because it's a fascinating fundamental problem. Whether or not it will lead to some technical or industrial scale advantages. Majoranas are interesting. That's why people like talking about them, like thinking about them. They are unusual. It is true that if created, it will be in some sense a new state of matter realized, and that they have unusual properties that none of the other known particles or quasi-particles have. It is also a fascinating multi-scale problem, material science problem, how to make a material good enough to convincingly show Majorana, an experimental science problem, how to measure Majorana in a convincing way, not with a flawed protocol that falls apart when you poke at it, but really that passes the test for real, like at least the test with your own eyes, that we look at it and say, this could be Majorana. And then, of course, it's a more esoteric, more fundamental question, but to prove that this thing is even non-abelian with low fidelity, but at least does something, some 3 sigma, 4 sigma non-abelian claim would be amazing, would be absolutely amazing. And so worth doing. And I think somewhere on par with some of the other fundamental projects out there in physics, like CERN's questions or LIGO. Side effects could be the creation of the World Wide Web or cell phone GPS navigation and things like that. Maybe it won't be topological qubits that we actually become useful for, but it's absolutely worth doing, at least for me, for a university scale. And we can do this experiment in a university setting. We don't need 127 authors.
I think that was a beautiful statement. I am still personally fascinated and in love with this physics, which is why I still want to keep coming back to it in one way or the other. I think we should keep it at this for us just talking, Sergey. There's a lot of questions and chatter in the chat. I think we should look a little bit at that.
So what I propose, thanks so much everyone and who is still around, but we would like to talk to you, but to make it more over a safe environment, I'm gonna stop live stream on YouTube at this point, so that we are not going on the record here. And we can even
Yeah, stop the recording
stop the recording.
in Zoom.